Hello, my name is Hadi Zamani from University of California, Riverside. Today I'm going to introduce SAOU, Safe Adaptive Overclocking and Undervolting framework for energy efficient GPU computing. First, I'll give you an introduction and explain our motivation, then I'll be discussing GPU undervolting and overclocking model. Also, I'll talk about GPU fault model and checkpoint and recovery methodology. I'll continue with evaluation, and at the end, the summary and final remarks will be provided. Modern GPUs with hundreds of computing cores make them well suited for HPC applications, especially for numerical computations and vector processing. Matrix multiplication is a heavily used and a key subroutine in many software packages, solving problems in linear algebra. Matrix multiplication routine is critical to the performance and power of high-performance LIMPAC benchmark (HPL) and many software packages solving problems in linear algebra, such as LOPAC, SCALAPAC, MUMPS, and SuperLU. For instance, MM-heavy applications such as HPL and SCALAPAC involves a time-consuming task to deal with computation, which is more than 90% of the computation cost. And Q+MM is a highly optimized CUDA package for matrix multiplication, which will be employed to do matrix multiplication. But given their high computational capabilities, the GPUs consume a significant portion of the total system power and energy. As technology advances towards deep submicron level, the static power becomes a serious problem. The static power can be reduced by lowering the voltage as shown in the equation. On the other hand, dynamic power can also be reduced by lowering both the voltage and frequency. With overclocking the GPU, dynamic power increases, but the execution time reduces. Hence, the total energy consumption may be reduced. So our goal is to explore the both undervolting and overclocking to save energy. What is Vmin and Fmax? Vmin and Fmax are the voltage and frequencies. That program runs correctly, but if we go beyond these points, system may experience faults. So we should tackle the possible faults with fault-tolerant algorithm, which adds overhead in terms of performance and maybe power. So we have to correct the potential faults. with an incremental and in-memory checkpoint and recovery technique. Even then, we show that we can save energy. The overview of SAOU shows how to find the appropriate level of undervolting and overclocking. This phase should be done offline in profiling phase, only once for each applications on the underlying GPU. As you can see, we start from the nominal voltage and frequency. Let's talk about voltage. We gradually increase the undervolting level. We run the program 100 times and record the outcome at each level. We observe the output then. As long as we only experience silent data corruption errors, which can be handled in application level, we increase the undervolting level. We do this until we observe other types of faults, such as segmentation faults, which cannot be handled in the application level. Similar to undervolting, we gradually increase the frequency of the GPU in steps of 25 MHz. We increase the frequency till we observe any other errors other than silent data corruptions. And then based on the failure rate model, we determine the number of checkpoints. This is the overview of SAOU framework. The failure rate of different applications due to undervolting are measured similar to approach used in Green MM paper. As shown in the figure, failure rate of application increases exponentially beyond Vmin. These values are different for different applications. For example, the Vmin for Q+MM is 10.2 and 23. This means even if all types of errors are in STC forms, which can be covered through a FT algorithm, we should design an algorithm which can tolerate more faults as we increase the undervolting level. This will increase the execution time and consume more energy, so there is no need to reduce the voltage further if the number of faults is going to be high. Various faults due to undervolting were thoroughly analyzed in the ICS 19, Green MM paper. But what about overclocking? We also experimentally measure each program's fault distribution and failure probability when operating beyond Fmax. To find sensitivity of overclocking, we also record error distribution of different applications during the overclocking. Silent data corruption, CUDA runtime errors, and OS crashes are among the notable types of errors the system may experience during overclocking. SCC refers to when program finishes its execution normally without any error messages, however producing a wrong result. These errors can simply be detected by comparing the results against the golden output. CUDA runtime errors, including segmentation faults and driver faults, are detected through a standard error output. OS crash happens when overclocking level is beyond the safe maximum frequency. Since SCC errors can be covered through a fault-tolerant algorithm, we only focus on SCC errors and we do not go for the frequencies which can cause errors other than STCs. The figures in this slide show the behavior of different applications, including Q+MM, FFT, black scrolls, and histogram with respect to overclocking. X-axis denotes frequency and Y-axis denotes fault types. Due to different activity patterns, we observe different STC rates. For instance, Q+MM and FFT have larger STC rates compared to the histogram and black scrolls. Now, according to the results from sensitivity analysis, we develop a realistic model to find the failure rate of the applications. PF is derived by counting the number of failures and dividing it by the total number of application runs. As shown here, we find the probability of failure for different applications as a function of overclocking level. Then we define reliability of T, reliability of application, or T, as the probability of that there is no failure in the system during the execution time until time T. The failure rate lambda is obtained using variable lifetime reliability model, a well-accepted model for transient and permanent soft errors. Lambda gives the number of errors per minute, as shown in the figure, where x-axis represents the overclocking level and y-axis represents failure rate per minute. Applications have different failure rates due to different activity patterns they experience during the execution time. Now, how to correct the errors. In case of MM, there are two main techniques, ABFT and checkpoint and recovery. The basic idea of ABFT is to encode input matrices with checksums. Based on the number of faults, we decide on the number of checksum vectors. We know that the other product matrix multiplications maintains the checksum relationship in each iteration of computation. At the end of computation and at each iteration, we check full checksum relationship again, and if the relationship doesn't hold up, then our result is faulty. Thereafter, faults are corrected. ABFT is not able to cover errors with more number of faults and with complicated fault patterns. So we are designing a low overhead checkpoint and recovery technique. What is checkpoint and recovery technique? Checkpoint is a snapshot of a system state, including a stack, heap, global, and register values. Checkpoint and recovery techniques usually relaunch the kernel from the beginning. This is a big problem in long-running kernels. We overcome this by modifying the application code to keep track of the necessary information. Also, we adopt an incremental checkpointing which preserves only the data that has changed since the last checkpoints. In matrix multiplication, we only checkpoint the partial results which are updated during the execution. To reduce the performance penalty, all the checkpoint data store. To reduce the performance penalty, all the checkpoint data store has been moved to GPU device memory. This avoids the expensive PCI Express bus transfer between CPU and GPU. So, as you know, in case of matrix multiplication, each thread block is responsible for a chunk of matrix. Since several threads are running concurrently, the memory inconsistency problem might occur if the threads share a variable in the shared memory. To ensure an appropriate kernel checkpoint and recovery, all threads synchronize before checkpoint and during the recovery. CUDA supports synchronization between threads within a thread block with a built-in instruction called sync threads. But the same problem exists if we extend this problem to threads within different thread blocks which share a global variable. Due to lack of any built-in synchronization mechanism between different thread blocks, similar problem might occur. To solve the synchronization problem between TBs, we propose an algorithm which synchronizes TBs before checkpointing. As shown in the figure, we define an array of global variables which can be accessed by all thread blocks. The array length depends on the number of TBs that can run at a time on the GPU. Before checkpoint module, we use sync threads to synchronize the threads within the thread block and make sure all of them are finished. Once all threads within the thread blocks are completely executed, we set the global variable corresponding to that TB to 1. Now, to solve the memory inconsistency between different thread blocks, we ensure all the TB flags are set to 1. Therefore, threads within different thread blocks will not modify the shared global variable anymore. So in SAOU, checkpoint and recovery is embedded into the code through a per-compiling phase at compile time. Since the GPU drivers are closed source, the modifications are done at the application level. During per-compiling phase, we transform application source code into a format where runtime support calls are inserted for constructing the computation state. In per-compiling phase, we follow the below tasks. First, we use buffer allocation to create buffers to hold the GPU state in the device memory, and then we insert the checkpoint locations. Then we invoke the kernel to run. Then we make sure we use synchronization mechanism to synchronize the threads within the GPU right before checkpointing. And then we decide to do checkpoint or go to the restore phase based on the detection phase results. All experiments were performed on NVIDIA GeForce GTX 980 GPU. For matrix multiplication, matrix with size of 10K was considered due to memory constraints. The GPU overclocking and undervolting was done using MSI Afterburner. In Linux environment, NVIDIA SMI was used to monitor the GPU utilization and report the power consumption in each 10 milliseconds. Due to memory constraints, the GPU cannot handle matrix multiplication of any arbitrary size, so we restrict the size of the matrix to 10K. This figure shows the number of faults for different pairs of frequency and voltage for the matrix with size of 10K. X-axis, Y-axis, and Z-axis shows the undervolting level, frequency, and the number of faults, respectively. For a matrix with size of 10K, on average, we estimate the number of faults equal to 1.45. First, we did an experiment to measure the energy gain due to overclocking alone in the presence of faults. As shown in the figure, at default frequency, there is negligible energy overhead of about 0.5%. However, as we continue overclocking, 5.3% energy reduction can be achieved at the highest frequency of about 1800 MHz. Beyond this point, segmentation fault occurs. Performance overhead is mostly incurred by detection phase. According to the experimental results, for a matrix of size 10K, the error detection time is 1.15% of the total execution time. For the same matrix, SAOU saves energy up to 12.74% just by undervolting till V mean. There is no error in the system till V mean as per our results. However, SAOU can save up to 20% with going beyond V mean and correcting possible errors with checkpoint and recovery technique. We also evaluated the energy consumption of combined undervolting and overclocking. X-axis and Y-axis denote frequency and undervolting level respectively. With combined overclocking and undervolting, we can save about 22% energy in comparison with the original system. In this paper, we propose an energy-efficient framework, SAOU, that reduces the energy consumption of GPU through undervolting and overclocking. Since going beyond the safe frequency or voltage gives rise to the faults, we designed an in-kernel, in-memory, and incremental checkpoint and recovery technique to handle these faults. We created an empirical fault model to determine the number of checkpoints at each level of undervolting and overclocking. For a matrix with size of 10K in Q plus mm, SAOU can save the energy consumption up to 22% through combined undervolting and overclocking without sacrificing the performance. Thank you so much for listening. I would be more than happy to answer any question.